Our next application is a mixing problem. We will do this mixing problem by thinking about a vat, a tank, that's got some water in to start with, and we got salt water going in. You can generalize what we're doing here to tanks that are other kinds of chemicals, and also maybe a little bit less clearly to maybe lakes and pollutants going into lakes, and pollutants being removed because of some of them going into some stream going away from the lake. The differential equation is not perfect. It's not going to take spatial effects into account. So it's maybe easiest to think of in terms of a vat. We've got a vat, a tank, but I like the word vat, that I draw like this, but other people draw it other ways. There's my vat, my tank. Let's say it's got a certain amount of pure water to begin with. There's my pure water. Doesn't it look so nice and refreshing? There's my 5 liters, say, of pure H2O at the beginning, no salt. All right, 5 waters of pure H2O at time 0, at the start, at t equals 0. Also, at that moment in time, you turn on a faucet up here. There's my drawing of a faucet. And, well, that faucet is attached to another tank that's got salt water in it. So you're mixing the salt water with the pure water. And just because you like performing experiments like this, you also open a drain and the mixture comes flowing out. You just like doing experiments like this, right? Just for the sake of doing them. That salt water coming in has got a certain flow rate. How fast is it coming out of the faucet? And a certain concentration of salt. Let's use particular numbers here. Let's say so this is salt water. Let's say the flow rate is something specific like 10 liters per minute. And let's say the concentration is, I don't know, 2 grams per liter. You also open the drain. The flow rate down here is some certain amount. It could be 10 liters per minute, and that will be the simplest situation. But just to illustrate that it can be something else, I will call it R liters per minute, where R is an unspecified constant, a parameter. And it's because of that unspecified constant is going to be why we need to use Mathematica to solve the differential equation instead of being able to separate variables. If I had used a 10 there for R, then I could separate variables to solve the differential equation that we get. But I'm saying maybe it's 10, maybe it's something different. What's the concentration, though? That is not so clear. It would be still in grams per liter. But what's the grams and what's the liters? It's changing over time, right? Because it starts out with pure water. The concentration at time 0 is 0. But then salt water is coming in and, well, let's make the assumption that it's instantaneously mixed. Instantaneously. I meant to snap it when I said the word instantaneously. Instantaneously mixed. Wait, how could it be instantaneously mixed? Because if we don't assume it, then it's too hard. Okay, if you like, you could pretend there are like fans inside here that are spinning, mixing up the solution rapidly, so that effectively the mixture is instantaneous. The concentration of the salt in the tank and the water is uniform at any moment in time. Now the concentration changes, but at any moment in time, it's uniform. The molecules, what, NaCl, to get my chemistry right, they're all spread evenly in the water. And they don't affect the volume either, right? There's so few salt molecules compared to water molecules that the salt molecules don't affect the volume. How many grams per liter? Let's call it, say, Q over V, where Q is the quantity of salt. Q is the quantity of salt in grams. It is a function of T, as a function of T in minutes. You don't see function notation here. I didn't write Q of T. You could, but for the purposes of the differential equation and making the slope field, it's actually better not to. It's better to leave it as a Q. The V, the volume, that's the volume of fluid, salt water, in liters. That is a function of T in minutes as well. It's unavoidable to write that one as a function of T. We have to if we're going to solve the differential equation, write V as a function of T. And it's easy to figure out. It starts at T equals 0 at 5 liters. And then it goes up by, well, or down by 10 minus R liters per minute. If R is 10, 10 minus R is 0, the water level wouldn't change the volume. But in general, this is going to be 5 plus, in parentheses, 10 minus R times T. If R is 10, then that's just a 5. But if R is something other than 10, then it's not a constant. So what's the differential equation? It's just like with the money, dq dt is rate in minus rate out. But now the units are grams per minute for everything. The derivative is in grams per minute. The rate in and rate out must be in grams per minute as well. Rate in is coming from turning the faucet on. Salt water flowing in. What do I have to do with these numbers up here? Think about the units. I'd like the liters to cancel, so I better multiply them. That would be 2 grams per liter times 10 liters per minute. The liters cancel. This simplifies to 20 grams per minute. What's the rate out? Multiply these two things. I'll put the flow rate first, R liters per minute times the concentration, which was Q over V. I will replace V with 5 plus 10 minus R times T. That is in grams per liter. The liters still cancel, and you are still left with something in grams per minute. It would be RQ over 5 plus 10 minus R times T. That's in grams per minute. So simplified, the differential equation written without units as dq dt is 20 minus RQ over 5 plus 10 minus R times T. That's the differential equation. If R equals 10, the flow rate is the same going out as going in, 10 liters per minute. Then this simplifies to 20 plus 10Q over 5 plus 0, which is 20 plus 2Q. Or minus, excuse me, minus. If R is 10. But R could be something different than 10. Okay, if it were this right-hand side, we'd be able to solve it by separation of variables. Not too much different than what we've done already, though be careful, the coefficient of Q is negative, and that would need to be taken into account as far as integrating. It'd be a little tricky. But if R is not 10, we got to use this. We need Mathematica for that. We don't have techniques to solve that. By the way, the initial condition is Q of 0 is Q naught is 0. There was pure H2O at the start. Pure H2O at T equals 0. No salt. This is our IVP. Let's have Mathematica solve the general one, as well as the special case when R is 10. We'll compare and contrast them and just see what happens. So I'm now teaching you how to use Mathematica to solve a differential equation. There's actually various commands that can be used. The one with the simplest output is called DSolveValue with a capital D, a capital S, and a capital V. This is a differential equation solver built in. Inside the square brackets, you need to put curly braces. Inside the curly braces, you need to start with your differential equation. Say Q prime of T for the derivative. Double equals, just like you use double equals with solve and find root. Contour plot. When Mathematica is doing solving work, you need to use double equal signs because single equal signs set things equal to each other, and you don't want that. You want to solve equations where the solution is unknown, so to speak, with double equal signs. If you use single equal signs, it'll get messed up. You'll have to quit the kernel to clear the memory and redo it with double equal signs. So I'm looking right here. Now I got a 20 minus, write the fraction, R times Q, though that's not quite right. I'll fix that in a second. Over 5 plus 10 minus R times T. What's not right about this? It looks like what I wrote by hand. Mathematica needs to have emphasized to it in all places where it's possible that Q is a function of T. So I need to put square brackets T here. That's something different than I do by hand. By the way, when I think about this by hand and think about the slope field, this right-hand side is a function of both T and Q. It's a multivariable function for the slope field. The slope field will not be constant along vertical lines as it is with pure antiderivative problems. It's also not constant along horizontal lines as it is with autonomous differential equations. This is neither a pure nor antiderivative problem nor autonomous. It's more complicated. But we could make the slope field if we wanted to. Next thing after a comma is to put the initial condition. Once again, use double equal signs. Comma outside the curly braces, emphasize Q as a function of T, comma, emphasize the independent variable is T, not R, for example. So when I enter this, Mathematica will treat R as a constant. T is the independent variable, and Q of T is the function. It's not very nice. Ready? 1, 2, 3, go. Yeah. Imagine finding that by hand. It'd be very hard. If you use / expand, it helps a little bit. It's a little simpler, though not much. If we plugged in R equals 10, it does become simpler because, once again, this thing here becomes 2 times Q. And it's a pretty simple function when R is 10. That one you could find by hand with separation of variables. But let's try to understand what's going on now by plotting the more general case. I'll just copy and paste. Oh, I love copy and paste. Copy and paste that whole thing in there. as a function of t, say t goes from 0 to, I don't know, 10 or something. Make a vertical plot range that's fixed, I think would be best. I don't know, 0 to 10. The Q, the output is the grams of salt. I put it inside of manipulate because I'd like to allow myself to change R. Now, I don't want to start R at 10, because if R is 10 in this formula, I'm dividing by 0 in these fractions here, and that would be trouble. R of 10 really is a separate case that I solved this way. So I'll start it at something other than 10, I'll 11 say, but I'll allow it to go less than 10, maybe down as low as 1 and as high as 20. So when I enter this, we'll see the graph of Q as a function of t when the R is 11, meaning water is going out faster than it's going in. R is the flow rate going out. Water is leaving faster than it enters. What does that mean about the graph? It increases before it decreases. That's what it means. Wait, does that make sense? Why would the graph of the amount of salt increase before decreasing? The water level starts out at 5 liters. Salt water is flowing in, but also mixture is flowing out. Salt water is flowing out. It's flowing out faster than it's flowing in. The water level's got to go down. The salt at time 0 is 0. We have to start out at 0. So, but after that moment, there is salt. It's got to go up. But it eventually has to go down because eventually there's no more fluid. It's all run out the drain. The concentration of salt is still going up, but the volume is going down to 0, making the amount of salt go to 0. On the other hand, and it gets more extreme if R gets bigger, although the scale there is different. It's, okay, I have to, let's do this with the plot range. So here's R's 11. If R gets bigger, it behaves more rapidly, you might say. Water's flowing out even faster. If R is less than 10, on the other hand, then the amount of salt grows. Until you reach the top, until the tank overflows. Then all bets are off. We're not thinking about when the tank might overflow here. Okay, so it's pretty powerful. Yes, sometimes people try to apply this, saying instead of a vat, we have a lake. And the inflow is pollutants from the rain or maybe the surrounding countryside, pesticides, whatever. And the outflow is from a stream that leaves the lake. Or maybe somehow you take cleaning the lake into account.